All right, this week we are talking about adaptations for aquatic life. So things that you need to live in water. And basically like some properties of water that make life in water good. If you think about it, all life on Earth started in water. So it all started in that primordial ooze, right? In the water. It didn't start for whales in the water, though. Whales are actually more closely related to cows and pigs if you look at the bone structure. Think about some of the adaptations that whales had to undergo to go from a life on land to life in water. What are some things that are different between cows and whales? Obviously, body shape, right? Cows have legs. Whales don't have legs. They have flippers and flukes, right? Also, whales are really streamlined, like fish. They have to live life underwater most of the time. So there's this thing called a dive reflex that as they go down, they actually slow down their metabolism and they shunt blood away from any of the non-vital organs to slow down metabolic processes. They also have a lot of hemoglobin and myoglobin molecules that hold on to oxygen, and so they have a really high oxygen carrying capacity. What are some other things? Where's a whale's nostril? It's on the top of the head, right? How about getting food? If you think about like baleen whales, the ones that have those combs that filter out any plankton or particles. Your tooth whales, like these sperm whales, they're able to echolocate. And so they developed echolocation. So there's lots of cool stuff that these animals had to evolve to go into the water. They have a lot of blubber, right? They have a lot of fat. They have that really thick fat layer to help protect their body from the cold. Lots of cool things whales do. So, I think our first question is, why did life start in water? Well, it has a lot of unique properties, one being its thermal properties, also the density and viscosity, and then its ability to dissolve inorganic nutrients. So let's talk about the thermal properties of water. So water has a really high specific heat. That means it takes a lot of energy to raise a little bit of water a little bit of a degree. All right? So we're talking it takes 1 calorie to raise 1 gram of water 1 degree Celsius. A lot of energy to just warm it up just a bit. It also conducts heat really well. So if you take one area and try to heat that up, so take like a rod that's hot and you put it in water, is just that area where the rod's touching, is that going to be the spot that gets hot? No, it's going to diffuse all the way through the water. And so water conducts heat really well. It spreads it out evenly, and so that local change gets stabilized pretty quickly. And it also resists state changes. So what are the 3 states of matter? You have solids, liquids, and gases, right? And so water in the liquid form is called water. In the solid form, it's ice. And then in the gas form, it's water vapor. So to take 1 kilogram of water, raise it 1 degree Celsius, costs 1 kilocalorie, right? So 1 gram, 1 calorie. 1 kilogram, 1 kilocalorie of heat energy. To go from liquid to gas, not only does it cost you that kilocalorie, it costs you another 540. So going from just regular water to water vapor requires a lot of energy. And then going the other way, going from a liquid to a solid, you're going to have to lose about 80 kilocalories of heat if you're a kilogram of water. So you have to lose a lot of that heat energy if you want to switch to a solid. Another thing that's really cool about water is it changes density with a temperature change. A lot of things change density with a temperature change. Typically, as things get cooler, they start to get more dense, or they get heavier. They come into each other. The molecules come a lot closer, right? And so they get heavier. Water does that up to 4 degrees Celsius. And so from 10 degrees Celsius all the way down to 4 degrees Celsius, that's the heaviest water you have. Then it actually starts getting lighter as you move towards zero. Water freezes at zero, right? So it becomes ice, and ice floats. And so at 4 degrees, this is the densest that water will be. So at the bottom of the ocean, what is the temperature in the water? 4 degrees Celsius. Right? In the bottom of a lake, in a deep lake, what's the temperature of the water? 4 degrees Celsius. Because anything higher than that is going to cause it to raise. Now, is that actually true? Kind of, sort of. Because as you add more solutes into the water, you can actually decrease the freezing temperature. Just think about, like, what do we do when we get ice on the roads? You throw sand and salt down, right? That salt dissolves into the water, increasing or decreasing the freezing temperature. So you can drop it below 0 degrees Celsius before it freezes. So, as we have the temperature going down, 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 the water's getting heavier and heavier and heavier, you hit about 4 degrees, and it starts getting lighter and lighter because the water is arranging itself to start forming ice crystals. And then once you get it frozen, you get a layer of ice. Ice is really cool. Like, it helps to insulate our ponds and lakes during winter. So when you have that layer of ice, it's actually acting like kind of like a layer of blubber on the lower parts of the lake. So that ice is actually protecting the animals underneath the water, which is really cool. So, density and viscosity is where we're going to pick up on the next one.